Good afternoon, everybody, and welcome back to the Energy Transition Week and to this session on the role of smart technology. My name's Janet Wood. I'm the editor of New Power, and I'm your host for the week. Those of you who were with us in this morning's sessions will have heard about the next steps for the various technologies we'll be using to reach net zero, some of which need new business models, for example, CCS, and considerable thought about what happens after the first of the kind plant, and some of the other technologies which need consumer buy-in. We also talked about some of the structural transformation that was needed. For those of you who were able to listen in to Chris Stark's presentation from the Climate Change Committee, and if you missed it, you can access it on the Carbon Trust website. You all have seen from that presentation that smart technology is going to be fundamental to our future. His rainbow graph, he said it was his favourite graph, showed that by far the largest part of decarbonisation comes from using low carbon solutions for heat, mobility, and all kinds of other sectors. That includes things like electric vehicles and heat pumps. This is important because, as the flexibility in GB report made clear, in the long term, we have to embed flexibility everywhere if we want to make the energy transition at least cost. We have to connect and balance between those sectors. Obviously, that raises all kinds of questions about delivery, and some of them I'm sure we'll get into in the discussion today. What are the local and national implications for deployment, and how can we ensure that there are benefits at every level? What can we do now to prepare for new technologies, new business models, new opportunities? How can existing infrastructure investments like smart meters play a role, and how can demand customers, from domestic users all the way up to major industry, be empowered to take a full part? As Hannah Evans said in this morning's session, we've made a massive investment in smart meter infrastructure. How should we leverage that? Of course, a lot of the response will come from industrial and commercial customers, but even within that group, there's a huge variety of experience and knowledge. Business customers include very small enterprises. It's equally important for them as for domestic customers that they see the energy transition as a just transition. Of course, it's already started, and I just wanted a couple of things to note how timely this discussion is today. Just today in my inbox, I had an email from BEMA, the Association of Appliance Manufacturers, who are supporting publication of 2 new standards for energy smart appliances for system architecture, and a second one for smart appliances for demand-side response. Also in my inbox, some warnings about how decarbonisation to meet the needs of rural communities will be very different from that of people in cities. So I'm especially pleased that we've got this discussion today and that we've included citizens' advice in the panel. Now, this is interesting because look where we are. Many customers have never moved suppliers. EV owners and heat pump owners may be very interested in variable tariffs and vehicles to grid, but I don't know how many are excited by insulation and a new hot water tank. For this group of participants, in this discussion about smart technology this afternoon, we can assume quite a bit of knowledge, I hope. But nevertheless, I'm going to go on and move on now to give you a few housekeeping announcements. The live sessions are shown on the On Now tab on the main event homepage. Once a session is finished, you'll be automatically prompted to join the next session on your screen. You can view the full event schedule for the week under the Agenda tab, or download a PDF from the Resources tab. You can leave and rejoin the event at any time using your email address and PIN code. And as I mentioned, the sessions will be recorded, and you can see them on the Carbon Trust website. To send in a question to our speakers, click on the Q&A tab on the right-hand side of the screen and press the blue plus button to add your question. All the questions will be anonymous. You can upvote questions by clicking the thumbs up next to the question. So that's pretty basic information for what I think are fairly expert participants, but that's the kind of simple information that you can't necessarily take for granted. I'll also mention a few of the phrases we've come to know and love from meetings during the pandemic. "You're still on mute" is probably the favourite. And the phrase, "Is that a legacy hand?" I'm sure would have been incomprehensible to most of us 2 years ago. If that all sounds a long way from the energy sector, it's not. It's the kind of challenge that third-party flexibility providers and people like building managers have to deal with in bringing customers to be active participants in the energy industry, whether they're large or small. Nevertheless, we're hoping that a smart technology is going to do the job of unlocking flexibility for us. And that's the issue we'll be discussing this afternoon. I'll just run you through how the afternoon will work. We'll be hearing a keynote paper first from Danny Pudjianto, a research fellow at the Imperial College London. Then we'll be hearing from Ollie Richards, Senior Associate at the Carbon Trust. Ollie's worked on a range of energy system projects and is a whole system thinker. He's also an energy system modeler. Ollie will be leading a panel discussion at 3 o'clock. And within that discussion, we'll be hearing from Chris Curry, who's head of flexibility at Bright Energy, and Jay Zollner, who's chief executive of Kiwi Power. And I'm glad to say we've also got Dara Rice, head of future energy services at Citizens Advice. So now let me hand over to Danny for the keynote presentation. Danny.
Thank you, Janet, for the introductions and having me this afternoon. Good afternoon, everyone. It is a pleasure to share some of the key findings from our collaborative work with Carbon Trust, focusing on the role of smart technology in minimizing the cost of energy decarbonization in future. I will start with the question, what is actually smart technology? So in a general term, it is a technology that meets its objective by monitoring and analyzing system conditions, optimizing decisions, taking the right actions within a certain set of constraints, and reporting the performance using measure indices. Some examples include smart electric vehicles, smart appliances, smart heating system with thermal storage, and electricity storage. I just want to reiterate that this is a technology that responds to system conditions in a smart way. This will transform the passive demand that we have now to active demand in future. Maybe some of the demands already transformed like that. From passive building to active buildings, where all these smart technologies are integrated in smart home energy management system. And this also interact with the local network operator, the distribution grid, but also interact with the transmission grid. So in a more specific context in the energy system, especially in the electrical system, the role of smart technology can be divided into a number of different functionalities. For example, like it can be used to reduce the peak demand. It can be used to do the energy arbitrage to use the low-cost resources, for example, when wind blows and it utilize more wind rather than curtailing the wind. So it can be used for that. It can also be used to provide system services like frequency regulations, reserve, voltage control, network congestion management, and can be used also to improve efficiency of the system operation, reduce emissions. So when there are a lot of low carbon energy sources, it's used during that time, and also improve the resilience. The studies demonstrate the need for flexibility from end users. And to achieve net zero, the use of renewable energy sources will increase from 30% to 80%. It implies that the bulk of energy will still be produced by large-scale plants like wind and nuclear, although we will also see the increased penetration of distributed generation. For example, the energy from offshore wind farms in North Sea will supply the energy demand across the GB, and some will be exported also through interconnectors. However, this increased share of RES in the energy mix will reduce the utilization of thermal plants that have been the traditional providers for the system services. Some plants may not be profitable to run and will be decommissioned, and therefore alternative sources of flexibility have to be available. Without those, the cost of maintaining the capacity and operating those thermal plants will be high. But thanks to the emerging smart technology, we can now have options for flexibility sources. But it requires careful technology designs and coordination across different system levels, as the flexibility from smart technology at the end users will affect not only the local energy system, but also how the national energy system will evolve. This underpins the research for the whole system approach and the transition for the local system operators to help harnessing these flexibility sources. So when we evaluate the value of smart technology, we have to consider all implications to the energy system, from local building, local energy network, up to the national system. Therefore, we have developed an energy system optimization model called iOS for many years and use this model for the FlexGD studies. The model captures not only the interaction from the supply side, national and local energy network, but also the interaction between electricity, gas, hydrogen system, heating, carbon removal, and storage technologies. It captures the interaction between system operation and system investment, the need to provide sufficient balancing capability in seconds to the capacity that need to be available to ensure sufficient capacity during extreme cold weather conditions when the energy system demand is at peak. It models a range of technologies and has option to use different heating solutions, such as electric heating, hydrogen heating, or hybrid systems, district heating, and thermal storage at local or district heating levels. It also models the carbon removal and carbon negative technologies, which are important to achieve net zero and offset the emission from sectors hard to decarbonize. It also considers the energy exchange and sharing of capacity and balancing resources with Europe through the interconnectors. Bearing in mind that the value of smart technology will be quite system specific, and there is uncertainty on how our future net zero system will look like. So we carried out studies using a number of different future scenarios. We studied 3 heat decarbonization pathways involving the use of hydrogen boilers, electric heating, and hybrid systems with a combination of heat pumps and boilers. Decarbonization heat will be a big challenge, as 60% of our energy demand in this country is related to heat. The strategy to decarbonize heat also needs to be synchronized with decarbonization of electricity and transport. To evaluate the value of smart technologies, we run the scenarios with and without the improvement in flexibility. With high flexibility, we increase the maximum deployment limit of interconnectors, battery storage, pump hydro, thermal storage, and demand-side response. Of course, the model also considers flexibility from generation and sector coupling flexibility from the hydrogen system with the hydrogen storage, carbon removal, and storage technologies. So this slide shows the results of the core cases we analyzed. It shows the annual system cost of the 3 scenarios with the hydrogen heating, electric heating, and hybrid heating with low and high flex in each of the scenario. The costs are broken down into a number of groups as shown on the legends on the right-hand side, from electricity generation capex, electricity network capex, including transmission distribution, OPEX of electricity, capex, OPEX of hydrogen CCUS system, capex of heating infrastructure, and cost of demand response flexibility as well. And it also takes into account also the estimate value of exporting energy to Europe. The range of system cost savings as a net across the core heating scenarios are between 9.6 to 16.7 billion per year in 2050. The results strongly suggest that investing in flexibility is a no-regret decision, irrespective of how we will decarbonize heat in future. The greatest saving comes from the electric heating scenario, owing to the high baseline costs driven by higher electricity peak demand, which drive more backup generation and network requirements, while the hydrogen and hybrid pathways, for example, have inherent flexibility, leading to less stress on the electricity system and then reduce their baseline low flex costs. The savings predominantly come from the reduction in the generation capacity and network investment avoidance, but they are also saving in hydrogen and the CCUS system. Now, the studies suggest that flexibility can come from different sources: heat, transport, and power. And this slide shows the volume of flexibility deployed by the model. We can see the share of flexibility sources from domestic and non-domestic sectors involving demand-side response, smart electric vehicles, including vehicle-to-grid capability, distributed battery storage and pumped hydro storage, interconnection and thermal energy storage at building, but also district heating levels. It is interesting to note that the thermal storage plays quite an important role here, driven by the use of electric heating. Even in the hydrogen and hybrid pathways, the off-gas grid and district heating customers using the electric heating. The results demonstrate that the decarbonizing heat with electric heating only will require the largest volume of flexibility here, including more than 80 gigawatt of distributed battery storage. Now, if you focus on the demand flexibility and remove other flexibility from the plot, the demand-side flexibility makes up a significant proportion of overall energy system flexibility. This implies that some additional investment will be needed at the end user side to support the system, and this value should be recognized. For example, to build sufficient volume of thermal storage, so when it is very cold and wind does not blow, the use of heat storage can reduce the heat-led electricity demand. Otherwise, significant backup capacity will be needed to meet the peak demand. It is also worth noting that the model operates all the flexibility in a fully coordinated manner. In a practical term, this will be a key challenge in the future on how all of these flexibility sources involving millions of devices and different energy systems can work together to support the system when needed and to avoid conflict. Appropriate system monitoring and control framework will be needed to be built. To demonstrate the importance of demand-side flexibility, we carried out a study using a high-flex system without demand-side flexibility using electric heating scenario. And the results are compared with the previous results, the low-flex and high-flex with demand-side flexibility. By comparing the cost of the second bar and the third bar, the deployment of demand-side flexibility actually can reduce the cost by 4.6 billion per year. This highlights the importance of enabling this demand-side flexibility. With the demand-side flexibility, the amount of battery storage deployed by the model can be reduced by 20 gigawatt. It also reduces further the investment cost in generation and network. So the results also suggest that there will be competition across different technologies. For example, like with the storage and demand side, if they have the same functionality, but also they have synergy across those, because they may also have different role to play. Therefore, having a portfolio of flexibility across the energy system manage the uncertainty and also reduce the cost. So this is my final slide, I would like to reiterate a few points from the presentations. First, investing in flexibility is no regret decisions, as it delivers material net saving in all scenarios we analyze. The savings will be system specific, of course, and it is more feasible in the electrification scenario, 16.7 billion, but the other pathways also produce a significant saving. The portfolio of flexibility across the energy system manages the uncertainties of smart technologies available in future and also reduces the cost. The third point is that the demand-side flexibility enabled by smart technologies is an important part of the portfolio, and it can reduce the cost by up to 4.6 billion per year in 2050. And the last point is that by embedding a flexibility in zero carbon heat and transport solutions, we also help to reduce their system impacts and costs. Integration of heat, transport, and electricity decarbonization strategy, therefore, is very important and should not be done in silo. Thank you for listening, and please reach out to us if you have any comments or questions, as it will be valuable to us to know your view and input on this study. Thank you. That's the end of the presentation. Thank you for attending.